Welcome everybody on Zoom. Welcome everybody in the lecture hall. Welcome everybody been watching us from the future. Today we are going to finish and completely wrap up on this lecture. It's mostly going to be about the Boyce code normal form and how to transform your data into Boyce code normal form. And then I'd say a few words about the other normal forms, but just briefly. Before we start, I would like to ask you a question to test your knowledge. And it is right here, makes you think a little bit. Which of the following are not unique? Multiple answers possible. Answer A is the closure of an attribute with respect to a set of functional dependencies, right? Or the closure of a singleton set of one attribute with respect to a set of functional dependencies. Answer B, the closure of a set of functional dependencies. To think about what this means. The minimal basis of a set of functional dependencies, that's answer C. And answer D, the superkey of a relation or relational table given a set of functional dependencies. So tell me what you think. Which ones are not unique? Some of them are unique, some of them are not unique. You might have several. Right, takes a bit time to think it through. Let me still show you what you said so far. Okay. Now we have one that interests the majority of you, another one. So two now have a majority. The majority is sometimes right, sometimes it's not. Let me close the votes. And the majorities are correct. So let's start with the first two because these are almost automatic answers because of the word closure. Whenever you say closure, there's the notion of everything you can reach, right? So a closure is unique by definition, right? So the closure of an attribute, it means you start with that attribute and then you use all the functional dependencies you can in order to add and add and add and add and add as many attributes as you can to the closure. The idea is really, remember this game with the secret tuple that I picked and hit. If you know that attribute, what else do you know? That is unique. It's everything else you know that is in that closure. The second one, the closure of a set of functional dependencies. This has to do with the rules derivations the rule-based derivations that I told you about last week when I gave you a set of functional dependencies. And then we have these actions that tell us how to derive new functional dependencies, right? For example, if I have A functionally determines B and B functionally determines C, then I can infer another one that is A functionally determines C, right? What is this one called, the rule? Start with a T. Transitivity, exactly. That's the transitivity rule. And there's a few other rules, all right? And the closure of a set of functional dependency means try to apply all the rules you can, everything you can to add and add and add and add new functional dependencies. It's actually going to be very, very big in practice, but it's unique. It's big, but it's unique. So there is only one closure of a set of functional dependencies. It's all the functional dependencies that apply, that are true given the initial set, okay? So these two are unique, the closures. Note that the first one, I said the closure of one attribute, but in general, you can also define the closure of a set of several attributes, right? That also exists. The third one, the minimal basis of a set of functional dependencies, it's actually not unique. It depends on in which order you apply the algorithm. And if I give you a minimal set to compute, maybe some of you will find a specific minimal set and some others will find a different one, right? So this is how it goes. You can think as an example, imagine that you have A gives you B, B gives you C, and C gives you A. That is one way of having a minimal set. But if you reverse the direction with the transitivity rule, you could get A gives you C, C gives you B, B gives you A. These are equivalents. These are both minimal sets, but these are not the same, right? So the minimal set is not unique, and it really depends on the order in which you apply the rules, right? In other words, if you want to tidy up a room, there's many ways you can tidy it up, and it's going to be tidy at the end. Then the super key, well, you know that there can be multiple super keys, right? There can be many of them. And in fact, this is why we try to select a few particular ones that we call candidate keys. It's the ones that are minimal in the sense that you can't remove attributes without them no longer being a super key. So it's not unique, right? And in fact, even the candidate keys are not unique. You might have multiple candidate keys, right? And then you pick, it's your choice, given what you think. One of the candidate keys will be promoted to the primary key. All right, so this is it. So let's then move on to the continuation. Other questions? Mm-hmm. I think in general, yes, it's possible to have two minimal bases that have a different cardinality. It would be nice if we could actually try to find a counterexample. We'll see if we manage to find that for you. But I see no reason why they would have exactly the same number of functional dependencies. It's the same for the super keys. You can have super keys of various lengths. And in fact, even the candidate keys can have multiple lengths, right? So this is why I insisted many times that when I say minimal, it's not minimal in the sense of the number of attributes. It's minimal in the sense of set inclusion, in the sense that you cannot remove any attributes without it no longer being a super key. Okay. So let me load the slides again. And that's number 6. Yeah. It's time. Okay. Here we go. So previously in information systems for engineers, we saw the first normal forms, which is just another word for atomic integrity. It means we only have atomic values. We don't have tables in tables in tables in tables that we don't have in the first normal form. Okay. The other thing we saw is the functional dependency. It's the idea that we have a functional dependency AB functionally determines DE. If whenever you have tuples that match on A and B, they must also match on D and E. And as a consequence, you can play these secret games where I hide a tuple and I tell you the value of A is bar and the value of B is foo bar. What is the value of D and E? And you can answer me. You can tell me D is false and E is 1 with absolute certainty. Then that's a functional dependency. Note the abuse of notations. It should be normally a set, but we just short-circuit it with just, we remove the curly braces, we remove the commas, we just say AB functionally determines DE, right? Okay, and then super keys, candidate keys, primary keys. A super key functionally determines everything. In other words, if I try to reuse fancy vocabulary, the transitive closure of a super key is the entire set of attributes of the table. For whom did that sentence make sense? The transitive closure of a super key is all the attributes. That's what a super key is, all right? It means if you know the super key, the values of the super key, then you know all values. Candidate keys are minimal super keys in the sense that you cannot remove any attributes. And that's because the super key can have as many attributes as you want, right? If you take all attributes, it's always a super key. So candidate key means you cannot remove any attributes. And primary key, you pick one of the candidate keys. It's your choice. It's your decision. Maybe a different person would pick another one of the candidate keys. But the primary key, there's only one, and that's the one you give in SQL that you ask the system to consider. All right. And then very quickly, actually, I only did them at the end for second and third normal form very briefly, but just so you know, everything that is in at least one candidate key, every attribute, we call it prime, right? So for example, in that example, car ID, canton, and number are prime because they appear in candidate keys. Car ID appears in the candidate key car ID, canton appears in the candidate key canton number, and number appears in the candidate key canton number. So these are prime, and holder and age are not prime. Okay, so that's another quick definition that I gave you. All right, then the closure of a set of attributes, it's the idea that you start with a few attributes. Here I start with A and B, and you try to throw in all the attributes you can, given the rules. You try to find a rule where on the left, you have everything that's on the left, but on the right, you're missing some of them, then you add them, right? So for example, you have A and B, that gives you C, it gives you D. Then since you added C here, now you can add B, you already knew it. You already have A and D from here, so you can add E and so on and so on and so on. And if then you go all the way, there is a unique set of all the attributes you manage to catch. And this is the transitive closure or the closure of a set of attributes. Then we have the actions and the rules. It's a way to derive functional dependencies. If I give you a set of functional dependencies, you can derive others in such a way that it's still equivalent. And we saw that it suffices to have just three actions: reflexivity, augmentation, and transitivity. That's all you need. The other actions are derivable from these, right? The other rules, I mean. Okay. All right. That's all we need. With this, you can actually compute the minimal basis, one of the minimal basis. It's not unique. You have multiple ways of doing that, but it's really about cleaning up, right? If I give you the set of functional dependencies on the right, you can clean it up in some minimal fashion and get something like what you have on the left, but you might also find other ones. Okay. Then what I showed you is what happens if we take a table and it has some functional dependencies and we project that table to some of the attributes, what happens to the functional dependencies, right? Well, in general, we have this very brute force algorithm that allows us to do that. We compute the power set of the attributes on the right. That gives us all the possible sets of attributes. We compute brute force, the transitive closure of these sets of attributes. We simplify, and we only keep the attributes on the right that are A, B, or C. Then we compute the minimal basis, and then we get what's on the right. This, in fact, is a beautiful way of wrapping up and using pretty much everything you've learned when you try to do these things. You use the minimal set, you use the closure of a set of attributes, and so on and so on, the rules. So it's a very good exercise, actually, if you want to practice a bit everything at the same time. All right, for whom is that clear, the projection? All right. Yes? B to A. I don't think you can derive B to A because you need B and C to have A. Do you agree? You need B and C to have A. B alone doesn't give you A. Do you agree? Yeah? All right. So basically, B and C, you cannot remove the C here. You can remove it on the right, but you cannot remove it on the left. All right? But thank you for asking. It's always good to criticize, to think critically. And there might also be once in a while mistakes on my slides, and then I fix them. All right. Now, because we projected, so this is when we project, but the reason why we want to project is in fact that we want to decompose it. We don't just project once, in fact, we project twice, typically. And we project on attributes in such a way that the union of the attributes in the projections covers the whole table. So it's a whole coverage. And at the same time, they overlap, right? In that case, they overlap with A. A is on both sides. And you're not missing any attribute. We have A and B on the left, C and D on the right, and a repetition of A. So it fulfills some of our criteria. Why are we doing that? We are doing that because we would like more tables that each do their thing, and we would like to avoid having a single big table that does everything. That's the very high level intuition. So we decompose it into these two tables. Now, how do I choose my decomposition? Because that's kind of arbitrary, right? I could also have picked BD and ACD, right? With D in common, or I could have picked ABC and ABD, right? That would also do the trick. So how do I choose how I decompose? I cannot do it in any way, right? I have to do it smartly. And the way we actually decompose is based on the functional dependencies. We look at the functional dependencies. The functional dependencies we don't like in terms of anomalies, because these are the ones that create the problems. It's the functional dependencies with something in the left that's not a superkey. For example, if I take A gives me B, this one is kind of problematic because A gives me B, but A does not give me everything. A is not a superkey, right? So I have a functional dependency that doesn't have a superkey on the left. The third one is okay, right? A and C gives me A, B, C, D, so that functional dependency is fine, right? But A gives me B, I don't really like that, right? Because this is going to bring problems in terms of anomalies. C gives me D, it's the same. C is not a superkey. The transitive closure of C is just CD, right? But not A, B, C, D. So C is not a superkey. I also don't like that. This is going to bring a lot of problems and anomalies. So in fact, there is a name for that. When we have this issue, we say that the table is not in the Boyce code normal form. And conversely, a table is in the Boyce code normal form if the only functional dependencies you have superkeys on the left. This is an example here of all the functional dependencies that you will find. They will have a superkey on the left. If you ever find just one, it suffices to have only one functional dependency that doesn't have a superkey on the left, then it's not in Boyce code normal form. Right? For whom does that make sense? For whom does that not make sense? Okay, you're following. Good. So as you might imagine, this helps us decompose the table because if I find a functional dependency that is not a superkey, I'm going to use this for my decomposition. And the idea, what I want to achieve, is I would like to take a table that's not in BCNF, Boyce code normal form. So if I have a table that's not in BCNF, what I want to do is decompose it by projecting into tables that are in BCNF, right? That's what I want to achieve. But I don't just want that because that would be too easy, right? I also want that if I do that decomposition into multiple tables and I reconstruct the original table by joining back the smaller tables, I need to retrieve exactly the same thing, right? So if I decompose the blue table into the red and green table at the bottom, if I join back the red and green table, that would be on A, it's a natural join. If I join them back, I need to recover the blue table, right? And in fact, if you decompose at random, then you're going to have a problem that it's not actually giving you back the original table. If you just project without thinking about how you project and decompose in this way, you join that back, you're not going to find the original table. This is why you need to use these functional dependencies that break the Boyce code normal form for your decomposition. In particular, that precludes a trivial solution because you might have remembered last time that the Boyce code, a table that is only with two attributes is always in the Boyce code normal form, right? If you have only two attributes, it's always Boyce code. So you might think of a trivial solution like, okay, why don't we just decompose our table so much that I just get tables with 2 attributes, right? This is what I get here. It's trivial. You can always do that, right? You just project into tables with 2 attributes. They're all in Boyce code normal form, finished, right? That doesn't work. It doesn't work because if you try to join them back, you're not going to recover the original table. That's why it doesn't work, okay? So again, we find the functional dependency that breaks BCNF. In that case, A gives me D, breaks BCNF because A is not a super key. You can see A doesn't give you everything. So we take A gives me D, and then if I take all the attributes in there, left and right, that gives me my first projection. I project to A and D. That's my first projection. That's just an example. If we had, for example, foo instead of bar, then the functional dependency would have been A give me CD. But let's just keep to that example. So I take that, and that gives me the first projection, a table with attributes AD. What about my other projection? I'm going to also have A plus all the other attributes. So basically, my 2 tables that I get, they overlap on what's on the left. That's not a super key, right? So they overlap on what's on the left, and then I have what's on the right in one of the tables and what's missing in the other table. For whom is that clear? Who could do it with any table? I give you a table, I give you the functional dependencies. There's one functional dependency that breaks BCNF. The left is not a super key. Who could do this? I see some heads. On Zoom, who can do it on any table? The same thing? We'll give you exercises. We'll give you plenty of exercises and you'll practice, right? So again, I repeat, just to be absolutely clear, I find the functional dependency that breaks Boyce code normal form. My first projection is what's on the left plus what's on the right. My second projection is what's on the left plus what wasn't in there so far. Okay, that's my projection. And then I project on AD and on ABC like this, right? It works. So now 2 things can happen. Either now I'm in BCNF, then that's fine, I'm done. If I'm not in BCNF, I just keep iterating and iterating and iterating. I just keep decomposing and decomposing and decomposing until I get tables in the Boyce code normal form, okay? And then I need to prove, if I do this, that I use the decomposition in this way, that I can reconstruct the original table by joining back the decomposed table. So normally what I would like to have is that the blue table joined with the red table should give me the green table at the top, right? By joining. In fact, it's true. If you do it this way, this is going to be true. Now, how do we prove it? Because that's actually very interesting to try to prove it. How do we prove that if I decompose in this way, the join gives me back the original table? Well, you know how to prove a mathematical equality of 2 sets, right? If you want to prove that 2 sets are equal, you prove that the first one is included in the second one, and then you prove that the second one is included in the first one, right? And then you've proven that they are the same set. So this is how we do it here. We prove first that R is included in the join. So if in other words, if I take a tuple in the original table, then it will be in the join of the decomposed tables. This is actually rather easy to prove, right? So let me try to do it just waving my hands. Let's take a tuple in the original relation, the one that breaks BCNF, right? So I take a tuple in there. That tuple is going to be projected on the 2 sides, right? So if I have the tuple that you see right here, then on the left, I'm going to have small a and small d as the values of my attributes. And on the right, I'm going to have small a, small b, small c as the values of attributes a, b, c, right? Who is following? Okay. Now, if I have on the left small a, small b, and on the right, small a, small b, small c, when I compute my join, these 2 tuples, they match on small a, right? So they're going to be joined back. And then I get small a, small b, small c, small d. And that is in the original table. Sorry, it is in the join. As a consequence, I've just proven that, right? I showed that A, B, C, D is in the join. Who agrees? Okay, you can also try to do it offline again, right? So in other words, if I take a table not in BCNF and I decompose it in that way, any tuple that I had in my relation will be in the join. So that side actually works. Now the tricky part is the other side. If I take some tuple in the join of the decomposed tables, was it in my original relation? Because otherwise I have a problem. Otherwise, the join would be larger. When I join back, I would get too many tuples. Too many of them, I would get tuples that did not exist in the original relation. This is what I want to avoid. But if I can prove that all the tuples I have in the join, they were in the original relation, then that's fine. Everything's fine. And it turns out that there is an algorithm called the Chase algorithm that allows you to prove that if a tuple is in the join, it's in the original relation. In order to do that, we do it like this. Imagine, let's assume that some tuple is in the join. I take any tuple in the join and I call it ABCD. ABCD in that case would just be variables, right? That call whatever was in the tuple I took. So I took some tuple that has values ABCD. It's in the join, right? I took it from the join. Now, if I took ABCD from the join, then it means that it came from somewhere, right? If it is in the join, then it must have come from the combination of a tuple on the left and a tuple on the right, okay? So it must have come from some tuple that had value A for attribute A and value small d for attribute D. What's in B and C, I don't know for that tuple. No, sorry, it doesn't have any. That's a tuple from the table AD, right? So I had a tuple with small a, small d. And I also must have had a tuple small a, small b from small c that came from my other table through the join. So I write it in this way visually, T1 and T2. My goal is to prove that ABCD was in the original relation, right? Now, this tuple on the left that had small a and small d, it's on the left because it was projected from the original relation. It means that there must be some tuple, T1, in the original relation that had small a in attribute A and that has small d in attribute D, and whatever in columns B and C, right? Because if I project that, then that gives me small a, small d. Now, because on the right table, I had a tuple small a, small b, small c, there must have been some tuple T2 in the original table that had small a, small b, small c, and whatever in column D. Okay? Now, I don't know if T1 and T2 are the same tuple. Maybe they are the same tuple, but maybe they aren't, right? So all I know is there is some tuple T1 that had small a, small d, and some tuple T2 that had small a, small b, small c. But we have functional dependencies. Remember, we know that the original table has a functional dependency. A functionally determines D. How can I use this here? Does anybody see it? Yes? Exactly, we can fill the blank. So if I give names to the ones that I don't know, it's typical to just put subscripts in here. So I call that B1, C1, whatever is in that tuple, and D2, whatever is in that tuple. Then you're right. I can use the functional dependency because here I have A and A in here. They match. So because of the functional dependency that A determines B, that's the one I used for that table, I can conclude that D equals D2. And because of that, I can indeed fill here, replacing this D2 with a B here, with a D, right? But look what happens. Now I have A, B, C, D. That's awesome. I have just proven that ABCD belongs to the original relation, right? That's the tuple where ABC came from. Who followed that proof? Awesome, perfect. So now we have proven that if I take a tuple in the join, then that tuple must be in the original relation. And if I combine that with what I said before, that if we take a tuple in the original relation, it must be in the join. That's the easier one to prove. Now I have proven equality, right? Inclusion both ways gives you equality. So I have just proven that because I decomposed in a specific way according to this rule right here, that I use my functional dependency A and D in this way. Because of that, I can use this chase algorithm to determine whether a tuple in the join is in the relation successfully, right? And bingo, it always works. If you use this algorithm with this decomposition of a table that's not in BCNF, you can prove every time with this algorithm that you recover the original relation with the join. In other words, it is a successful decomposition. It doesn't matter if you take the original table or the smaller tables, they have exactly the same information. Okay. All right, so what do we have now? We have an algorithm that allows us to decompose a relational table that is not in BCNF into tables that are in BCNF, and it's lossless, right? Lossless means that the join recovers the original table. So it's a lossless join. The third thing we wish we had, it would be nice if we had that, is that if now we project the functional dependencies of the original table to the smaller tables, it would be nice if we have exactly the same functional dependencies. The problem is that it's not true in general. Some of the functional dependencies that we might have had in the original table might get lost. For example, let me just to give you an example. Imagine that we might have had a dependency that says C functionally determines A, right? We might have had this functional dependency in the original table, but we might lose it. So in that case, we don't. Let's say C functionally determines D instead. So C functionally determines D. We lose in the decomposition. Why? Because we don't have any table with both C and D. So I lose that functional dependency. Okay, who understands that? Right. So if I have C determines A, I can project it to the right. I still have C determines A. If I have C determines D, which is true here, I cannot project it in any way because I don't have any tables with both C and D at the bottom. So I'm losing that functional dependency. Okay? And in general, I have this impossibility triangle that I cannot get the three of that. So in our case, we managed to put everything in Boyce code normal form. So we don't have any anomalies anymore. We cannot have any issues anymore at runtime. The join is lossless, meaning that if I join back the decomposed tables and I get back exactly the original relation, but I might lose a few functional dependencies along the way that I might have had on the original table and that I cannot keep when I decompose, right? So if you use other normal forms than the Boyce code normal forms, you might get other combinations. For example, you might go to what we call the second and the third normal form. They would also be lossless if you decompose them, but they would preserve the dependencies. However, you no longer eliminate all the anomalies. If you try to convert to the second or third normal form, you might still have a few issues with anomalies. So you can't have all three of them. It's really a choice to make. This is obviously a no-go, right? You don't want the join to not be lossless because then you're basically corrupting your data if the join doesn't give you back the original data. All right, so this is basically the conundrum that we have. But typically, again, and for the purpose of this lecture, this is where we are. We target the Boyce code normal form. First, because the definition of the Boyce code normal form is actually very easy. It's only about having super keys on the left, the functional dependencies. It has the advantage that if you manage to convert everything in Boyce code normal form, you don't have anomalies anymore. That's a pretty nice feature to have. We can prove that the join is lossless with the chase algorithm. And losing a few functional dependencies, we just live with that, right? This is a consequence that we just accept. All right. You will have plenty of exercises on that, and if you look at past exams, there are plenty of exercises where we give you functional dependencies. We ask you, is it in Boyce code normal form? Is it not in Boyce code normal form? We give you also the chase algorithm with some tables, and then we ask you to fill that in order to practice. So you really have a lot of exercises to practice in order to get acquainted with that, right? It's really something, once you do it and it becomes mechanical, then it becomes crystal clear to do. This is something very practical, okay? So that means concretely that even if today you didn't catch everything, like maybe not everything is clear, doing the exercises will help you. That will make it clear, okay? And that is my last slide, where I just throw at you the second and third normal form. Why am I doing that? Because they are not so important for this course. I'm just mentioning them, but that's not the focus. The focus on this course is really the Boyce Code normal form. This is the one that we focus on. But just so you know, there is less strict normal forms called the second and the third normal form. The first one, you know that's the atomic the atomic integrity. But in fact, there's a simple way of seeing why the second and third normal form are less strict than the Boyce Code normal form. So let's first go to the third normal form from Boyce Code. So again, the third normal form is less strict. And the way it's less strict is that, you know, that condition that an attribute cannot depend on anything that's not in a super key, right? That's not a super key. That basically means you can only have super keys on the left of your functional dependencies. In the third normal form, I basically don't mind if I have a functional dependency with something that's not a super key, when on the right, I only have non-prime attributes. Then that's fine in the third normal form. So I'm a bit less demanding. I tolerate to have something that has something not a super key, determining something that's a non-prime attribute. Remember, the non-prime attribute, it's those that are not in any candidate key, right? All right, so this is why it's slightly less strict. And then if you go down to the second normal form, you keep the non-prime attribute thing, but you tolerate even more things. You tolerate something that's not a super key, but the only thing you don't want is a subset of a candidate key, right? So a strict subset of a candidate key is not a super key, because by definition of a candidate key, if you take a strict subset, it's no longer a super key, right? Because by definition, it's a minimal super key. So basically, the second normal form is more tolerant, is going to accept functional dependencies that have something that's not a super key, as long as it's not a strict subset of a candidate key, and that goes to a non-prime attribute, right? So it's less strict. It doesn't matter if this is clear or not, or if you understand that or not, because again, that's not part of the material. I just wanted to show you the idea that we have the first normal form, then the second one is stricter, and then the third one is even stricter, and then Boyce Code is even stricter. This is the one thing to remember, right? Okay, that's it. And again, only the Boyce Code normal form and the first normal form matter for this course. Everybody on the page, on the same page? Okay. We have a few minutes to go before the break. I'll start with the next part. Who has the feeling they're with me on this? Okay. More or less, okay. It's complicated, right? It's very formal. It's a lot of things to digest. But again, my advice is solve the exercises. This is really the secret. If you solve the exercises, if you practice with the past exams, you will see that it will become automatic and mechanical. Yes? No functional dependencies at all, then it's in Boyce Code normal form. Because in order not to be in Boyce Code normal form, you need a functional dependency that breaks the rule. If you don't have any, then you cannot break the rule. So then you don't have any problem, basically. Does that make sense? So the starting point is really, if the table is in Boyce Code normal form, there is nothing to do, right? If it's not in Boyce Code normal form, necessarily you will find a functional dependency that breaks BCNF, right? And once you find it, you use that to decompose in this way, right? Using a first projection with both sides of it and a second projection with the left-hand side plus the rest, then you decompose in this way, right? And what's really, really nice is that we can prove that when you decompose in this way, joining the two gives you back the original table, always. If you took a rule that breaks BCNF, you always get back the original table with the join. Okay? And in your case, so if you don't find any functional dependency, then you just don't decompose. You keep the original table and that's fine. Okay? Any questions in the room? Clarifications? On Zoom? All right. And of course, you know, there is the discussion forum. We can monitor your questions. We will answer any things to clarify. I also recommend that you read the book. Who reads the book so far? Databases, the complete book. There's basically a chapter every week. It's pretty much the same thing I'm telling you. It's the same material, but it's really, really useful because then you get two angles, right? You get the angle I give you in the lecture, you get the angle from the book. And in fact, some of you might have a very visual memory, right? So in that case, just reading from a book might help you consolidate the knowledge, right? So there's the lecture, there is the book, and the two are complementary, right? Okay. So I'm going to move on to the next part. It will be easier. Don't worry. This was so the database design theory that was really the core of the course. That was the toughest, and you survived it. So now all you need to do is practice.